Hi, welcome back to AP Chemistry with Mrs. Mays. Today we're looking at infrared spectroscopy. It's another way of using light to see small things. So infrared is basically the part of the electromagnetic spectrum that is below the visible red. So it is a higher frequency than radio waves, but lower than visible light. That means it also has a higher amount of energy in every wave than radio waves do. These waves then have the energy to push or pull the nuclei within the molecule. And this leads to bonds stretching, compressing, and bending. Or sometimes we call this vibrating. Here's a picture of what that might look like if bonds stretch asymmetrically or symmetrically, or if they rock back and forth, or sometimes they scissor. They go towards one another instead of going the same direction. But it's the absorbance of infrared radiation that is causing this motion in a molecule. We say it excites a molecule and gets things moving around. They vibrate faster and more energetically than when that molecule is in its ground state. Imagine that a bond is like a spring. Strong bonds are like stiff springs, and they would vibrate more rapidly. Heavy nuclei are like heavy masses attached to our spring, and they would vibrate more slowly. We can distinguish one type of bond from another. Molecules can only vibrate with discrete energy levels. That means not every energy makes the bonds move like this, only certain ones. So here's how we might use it. A bond between two particular atoms, say a carbon double bonded to an oxygen, will vibrate at nearly the same frequency in any molecule in which it is found because that CO bond is distinctive, especially with a double bond. So we can look at what frequency it vibrates and we can look for it to see, is it present? Like in ethanoic acid, we have the COOH, and here it is. We know it's there, and we can look at the frequency and find it in about the same place every single time. Because it shows up in about the same place every time, the infrared spectrum is a series of bands from each different functional group or portion of the molecule. And we use it as essentially a functional group detector to find out which groups are present in our molecule. So let's look at the infrared spectrum of propionic acid. Not sure if that's how you say it, but what we know is propionic, whatever, has 3 carbons, right? And then, of course, we'd have the carboxyl group at the end. So normally, we would be looking for a couple of different things. First of all, this carboxyl group that makes up an organic acid, the COOH, has 2 characteristic IR absorptions. So when we see both of those, we suspect the presence of an acid. We have pretty good evidence that we've got an acid when we have the CO stretch, the double bond stretch for CO, and also if we see that OH stretch, which occurs up here. But what's kind of weird in propionic acid is that the hydrogen bonds between the molecules cause dimerization when it's in a condensed form. The molecules begin to stick together into not monomers of propionic acid, but actually group up into groups of 2 called dimers. So the monomers join together into groups of 2 called dimers, and what that does in our spectrum is that it changes the frequency or the amount of energy of the stretch. So here's what we would normally see for the monomer, and here's what we see for the monomer of the CO stretch. So it's shifted a little bit to have some more energy than normal, but it also intensifies the peak when you have a dimer versus a monomer. So this is how we might use infrared spectra. We look at the types of functional groups in organic molecules, and we can detect which ones are present.